gave me the invitation to come here, and coming from a mathematician, well, I should say not any mathematician, a mathematician's mathematician, I realized quickly that actually there was not a misspell in the title of the workshop. There should be some mathematics involved. There will be some mathematics involved, but not only that, there will be some, take-home message that each and every of you can take away with them. So I'm going to talk about electrification of the energy sector and its impact on power systems. Electrification actually is a means of decarbonizing, but it has, consequences, and I would like to know, whether, it's doable or not, how far can we go in this electrification. So the background, the motivation, of course, we all have seen this plot here. I don't need to comment too much on that. This rise in temperature here is the fastest ever, going up. There probably were temperatures going down that were faster than that after, like meteorites or extreme events like that. But here we really have our planet that is boiling, and that has consequences as we know them. I show you here two maps, one of the same place, one from 1972, one from 2022. 50 years of difference, please. 50 years of difference between these two. Look at this place here. This is the Oberalech-Hütte. It's a lodge in the mountain, and it was, quite conveniently placed right above the glacier when it was constructed. And now the glacier is 200 meters below. And you can see that, been there. If you take a picture, that's the Oberalech Glacier here. And you see that all these rocks are not oxidized. Not so long ago, not so far away in time, they were covered by ice. And one of the unwanted consequences, that lodge is somewhere around the rock here. When you go to the Alechhorn, the first thing you do is go down 200 meters, which is not good to start a hike. And of course, these 200 meters, you have to do them at the end of the hike. So that's not good either. So, we need to do something to actually save this part here, at least, if we still can. All right, so how are we going to do it? We know who is the usual suspect here, right? That these are greenhouse gases emission, CO2 in particular. Who is emitting them? And of course, compared to the nice talk of Julia Steinberger this morning, there are different ways of counting different economic / human activities. Here you have energy that makes up for about 3/4 of the greenhouse gas emissions. How does it do that? Well, basically it burns fuel. It burns fossil fuels. It burns fuel to power cars. It burns fuels to, heat buildings, stuff like that. If all these processes could be converted into electric processes, we may have a chance to actually decarbonize human activities here. So that's what I want to do. Well, that's not what I want to do myself, but I want to investigate these things. And 2 or 3 years ago, this student, Julien Michelot, who is now a PhD student at the University of Geneva, did this study of how to decarbonize Switzerland. Now, of course, we were very conservative in the time scale. We went all the way to 2060. Hopefully we can compress that to 2040. So let's not look too much about the horizontal axis. Let's look at the vertical axis. What does it take to actually decarbonize? Well, here to here, that's fossil fuel burning, either to power cars for transportation or either to heat. Okay. To heat. We want to bring this down to zero. And that's what we did here. How do you do that? Well, your cars, you can have electric cars. heating buildings, you may have heat pumps instead of furnaces that burn fossil fuels. If you have heat pumps, you have to take the heat from the environment, which is why this thing is increasing. This is renewable heat that goes up. And if you have cars that are powered by, well, electric power, then electricity consumption is going to go up. It's not going to go up by much. I mean, it's going to go up by 50%. Right? Compared to 50, about, give or take something. I mean, there are many such investigations, and they all end up with some similar results. Why is that so? I mean, if you look initially, you had like 60% that was burning fossil fuels, but there's, energy efficiency in electric processes. Energy efficiency means, for instance, that, your car, the energy that is contained, that is stored in its battery, is about 1/4 what is necessary for a similar-sized car with the energy content in its fuel. Basically, a gas-fired car is heating up the atmosphere. And then it's also moving. Okay, so energy efficiency helps you to bring down your energy consumption. It brings down, part of the energy that you're using is taken from the environment for free, which is good. You no longer emit greenhouse gases, that's nice. But there's a price to pay, which is increasing electricity consumption. So, electricity is part of energy, but it's not all of energy. We reduce energy consumption, we reduce emission of greenhouse gases, of course, provided electricity is produced by renewables. And the problem is about increase of electricity consumption. More consumption meaning more production. What is the impact on the power system? Yes?
I have a question. You suppose that the hydrologic power is stable, but with the climate change, don't you have differences on the...
Some say it's going to go up, some say it's going to go down. We basically take this thing here as indicative. It's indicative. What's that?
What is going to go up or down?
Hydropower.
Ah, okay. Maybe I can just add some information about that. What we expect is that we will mainly have a change in the season for the production from hydropower, but not on the total amount for the year. So there might be problems at some time in the season, but not globally.
Of course, one thing we won't have anymore, and this year it has been producing a lot, is the melting of the glacier. Once they melt, they'll melt. Okay.
Sorry.
Yes.
In terms, for example, for cars, in terms of construction, is it less or more polluting to construct electric car? Sorry. When I can have an electric car or a fuel car, but I have to, in both cases, I have to build it, to construct it, to produce it. Is it more or less polluting to produce an electric car than a...
We are going outside of the scope of this talk, but okay, to make a long story short, there are lobbies that probably tell you that an electric car is, very polluting when you build it. And this has been partially at least debunked. And I can give you a link to a movie that actually goes step by step into those things. Okay, so electricity generation should not emit greenhouse gases. We want clean energy production. What do we want, for instance? Photovoltaic. Okay, you put solar panels so that you, for instance, here the case that was studied was you produce the same energy that nuclear power plants in Switzerland produce. What do you have? This is the production of nuclear power plants. This is the production of solar photovoltaics in a week in the summer. Okay, they are calibrated so that over the year they produce the same. There are fluctuations, there are daily fluctuations, but on top of that there's more sun in the summer than in the winter, so you have these 2/3, 1/3 seasonal fluctuations, roughly speaking. It may be 60-40. Okay, so you need to take care of that. Then you need, perhaps, to have wind turbines. They fluctuate even more. You see them going up and down to full power and down. You have these huge fluctuations that are characterized by some sort of stochasticity. I mean, the wind is flowing or not, and it can stop very fast. Okay, and that's when we can summarize the problems that is facing the future power grids. On the one hand, so far we've had big centralized generators, and on the other hand, we will have decentralized generators, photovoltaic panels on your roof. On the one hand, you have power plants that are dispatchable. You can tell them when to function and when not, or at least you know when they will. And you replace them with very uncertain productions. And that is scaring a lot of people, including experts in the field. Now, this expert, he uses a particular jargon, so let me translate it for you. He's worried that actually these fluctuations may jeopardize the stability and safety of supply of the power grid. But variability and uncertainty are nothing new for grid operators. Can anyone tell me what this is? It's a load curve of some country. So which country? 30 gigawatt is a bit too much for Switzerland. Then you look at the time, this is in the low side of the consumption. So it probably goes up to 50 gigawatt. Switzerland being like what, 8, 9? 50 gigawatt is 6 times Switzerland.
France?
US.
No, it's not US. US is way above it. I mean, you cannot multiply. US you multiply by the difference in population and another factor of 3.
Italy.
No, another same size.
Spain.
No.
Netherlands?
Someone said England. It's England. Next question. What happened here?
Television.
Exactly.
I thought the news on television.
There was some news on television, yes. A news that lasted, 45 minutes, then 15 minutes break, then 45 minutes, then 10 minutes break, then 30 minutes. Soccer. Okay. Now you see here, it's funny, but it's for real. The grid operator had to take into account that suddenly there would be, or not, 2 gigawatt, that is about 10%, between 5 and 10% of the consumption going up in what? In 10 minutes. By the way, why is that so?
Making tea.
Making tea. Same game in Germany, you see nothing. You open the fridge, you take a beer. And here you have 3 gigawatt almost. That's 3 million kettles. That's tea. Okay, so, all right. So this is funny, of course, but I mean, grid operators know about that. They know about these things. They get ready for it. What you need to actually absorb this type of fluctuations is simply, to have enough reserve and be on the lookout. And they are on the lookout. And you just need to adapt the reserve that you have. Yes.
How do they do this? Do they just get a gas start?
So I don't know which power station was actually turned on, but I suspect for Britain it was gas, most likely. Okay. Okay. So you need to have that. So it's not such a big deal. What you can do is actually put, more, and this is the type of, this is the similar time scales as timescales of fluctuations of wind or solar. So what you need to do is just be ready, have enough reserve to actually absorb these productions. And I'm not saying everything is fine, but in a nutshell, technological solutions exist. And they've already been implemented in different contexts. Okay, so now I want to be a bit more quantitative. So far, what I said about this decentralization and these non-dispatchability of this production, well, it's not a big deal, meaning we can deal with it. I want to guide you through what I think is the real challenge. And for that, I need to be a bit more quantitative. So I'm going to talk about electric power systems, what they are, and I will model them mathematically. So, when they were first constructed, power grids, it was realized that actually, to transmit electricity over large distances, either you have large losses in the lines, or you bring up the voltage. You transport electricity at high voltage. In order to do that, you need you need transformers. Transformers bring you from one low voltage to some high voltage or vice versa. Why so? Why do you need transformers? Because you cannot consume nor produce electricity at very high voltage. You will have all kind of sparks and discharges and stuff like that. You don't want to have that in your kitchen. Okay, so then what that means, by the end of the day, you have different levels in the power grid, from big suppliers to extra high voltage, medium voltage, low voltage, 7 levels including the transformers. That's how people model them. And we want to write an equation for that, how it works. And to do that, we need first to identify what is the quantity that is going to be expressed in that equation, and the quantity is power. Why is that so? It's because when you transform electricity from one voltage level to the other, power is almost conserved. There is an efficiency of these transformers which is 99 point something, and as a physicist, less than 1%, you neglect it. Okay, so I'm going to write an equation for that, and my starting point is going to be Ohm's law. I assume that all of you have done a little bit of electromagnetism. It's a linear relation between current and voltages. So I have my power grid. This is the Switzerland's high voltage power grid. And each of the small dots you see here are nodes where you actually either connect that high voltage power grid to lower voltage levels or connect it to a power station. For instance, here, you have big hydraulic power stations in Chamozon and Chandolin, and you have nuclear power plants. Where is that? Okay, Leibstadt is here, and Gösgen is there. Okay? At each of these nodes, the variables are voltage. I labels the node. I have 100 and something nodes here, and VI is the voltage at that level. It's an AC power grid, alternative current, meaning there will be a phase and an amplitude of that voltage. Okay, and at each of the node, either I inject current or I consume current. It's either a producing node or a consumer node. So I have the current there. And in between two of these nodes, if there is a line, there is a Yij, which is called the admittance of that line. It's a quantity that relates voltage to current. Okay?
It's inverse of resistance?
Admittance is resistance plus, is conductance plus susceptance, plus I times susceptance, where I is square root of -1. I didn't want to go into that. But we have an AC system, so it fluctuates, and then you not only have resistance or conductance, which is its inverse. You also need to take into account the imaginary part of the admittance.
Sorry, I have a question. So the index set is what over all the nodes in the graph, or?
The what set?
The index set.
The index set.
Yes, that's right.
Okay.
Yeah, all the nodes there. Okay, So now,
What's the difference between the red lines and the green lines?
oh, we have two different voltage levels. At very high voltage, we have 220,000 volts in green and 380,000 volts in red. Okay.
Sorry, the green and the red is independent of the VI and YIJ?
The rated voltage is different in the green than in the red. There's a factor of square root of 3 between them.
Okay.
You're not asking why square root of 3?
No, I'm not
I can
trying to
give-
understand. So each node has a color, and each node has a color, a voltage, and a current injected at it, right?
Yeah. But let's not go into that. You know, next time I'll show it in black and white.
Okay.
You know, it's a graph.
So the values are uncorrelated to the color?
Sorry?
Are you saying that the values are uncorrelated to the color?
The what?
The values VI
Yeah, the VI is correlated to that, yes.
are
Okay,
they
the
correlated
VI
or
on
uncorrelated?
the green nodes is about 220,000 volts, and it's 380,000 volts on the red ones.
So why square root of 3?
Was that?
Why square?
No, don't talk the two of you.
Why root 3?
Why root of 3?
Oh yeah, okay. Look, for those of you who are still interested, at the end of this talk, I'll give you the answer. It has to do with transformers. Okay, anyway. I want to have an equation for power. So what I do, VI is a complex number. It has an amplitude and a phase. So I multiply the vector of voltages on all the nodes with the vector of currents, as indicated here. This is a component of the vector of current. There's as many components as there are nodes on my network. And I take it complex conjugated. If I do that, I have a real and imaginary part of that quantity. The real part is called the active power. The imaginary part is called the reactive power. And I'm not going to go into too many details of what it is, but by the end of the day, this is the equation that you get with that procedure.
So, sorry, what's S?
S is this scalar product.
Oh, okay.
And so, taking an equation for the real and the imaginary part, you get these equations here, which are transcendental equations. They can be solved only if you have like very few nodes, very simple systems. So usually you rely on numerical methods to solve them. But by the end of the day, the goal is to have the state of the system given power consumptions. Let's say, forget about reactive power. Let's take just the real power consumption and production. So the total amount of power produced is going to be equal to the total amount of power consumed plus the losses on the lines. The losses are here. This is the conductance inverse of the resistance here. Okay. And if you solve them, by the end of the day, what you have is on each node, you have the voltage amplitude and you have the voltage phase, and you know exactly the state of your system. And you know in particular if that state is acceptable. And so this is a calculation that is done in real time, all the time, by grid operators. And they look at it, is it converging? Is it fine? And if it is fine, they let the grid in that particular state. But sometimes it is not fine. And so we need to look at the dynamics of these systems. Now, the dynamics of these systems, if you want to understand it qualitatively, look at the dynamics of the generator. So you have here this hydro plant. You have a turbine. The turbine rotates. It makes the alternator rotates, which actually makes electricity, Faraday's law, and inject that electricity into the grid. Why does the turbine rotate? The turbine rotates because there is an input of energy. So these machines, what they do is transformation of energy. Either you have chemical, mechanical, nuclear, or thermal energy that goes into your turbine. Turbine rotates, alternator rotates, electricity is injected into the grid. And now the equation that governs the dynamics of those systems is given by an energy balance for the rotator, for the rotating machine. rotating machine has some kinetic energy of rotation. You all know what is kinetic energy of rotation?
I vaguely know, not well. Like I would trust
It has
myself.
more, it has more kinetic energy of rotation if it rotates faster, and less if it rotates, slower. Let's leave it at that. At this time.
And it's quadratic.
And it's quadratic in the good job. And it's quadratic actually in the angular frequency of rotation. Okay. Now, if there is suddenly more water flowing faster into the turbine is going to accelerate. Or if suddenly the grid is actually consuming more, there's a tendency to actually suck up more energy on this side, so the turbine is going to slow down. And so there is a coupling between this energy balance and the rotation of your rotating machines. And the last thing is that the rotating machine, its frequency is directly related to the frequency of the electric current on the grid. So there is an electromechanical coupling. If you want to know whether there is enough energy injected into the grid, you just measure the frequency of the power grid anywhere you want. I should have taken it with me, but we have devices. You plug them into the grid here, and you look at the frequency. And you can see the frequency fluctuate. So this is the energy, the equation. And it's basically obtained by a balance between power in, changing the kinetic energy here, and the power out. If power in is equal to power out, that means Pi is equal to this. You recover the transcendental equation I had before, and the frequency doesn't change. First derivative of the voltage angle is the frequency, second is the derivative of the frequency. Okay, so I think I already said that, and I can move on. So, the grid operator is very happy about that. That's one, nice consequence of having AC power grids. You just measure the grid frequency. If it's at 50 Hertz, you don't do anything. Everything is fine. There is enough production, just enough production to satisfy the consumption, the loads. But if suddenly you have more demand and less generation, the frequency of the grid is going to come down. You measure that and you see that there is a problem. And eventually you can identify the problem and correct it. Ask, some power plant to produce a little bit more to compensate for that. Okay. It is measured. Actually, it is measured by Swiss Grid for the European grid. And these are all data that they used to be on their website. And you see that over a period of 3 months, 2 months and a half here, the frequency was oscillating between 50.1 and 49.9. So it is constantly moving up and down, slowly, steadily, no problem. Now this is a relatively long time scale, so let me look at shorter time scale. This was today. You see that I finished my talk at around 2:30. Okay, and you see that it is not moving over time scale on the order of 10 minutes. Now, if you look at the time scales of this equation, you end up with time scales which are between microseconds and seconds. So obviously, in this situation, you don't care about the dynamics. Just look at the steady-state situation using the power flow equations. So when do we need this type of equation here?
Your time.
When what?
When something bad happens.
When something bad happens. Like what?
A power line is interrupted.
Okay.
British people go for tea.
Sorry?
When British people go for tea.
And someone becomes a massive missile strike.
Yeah. Either you have a power line that is open, you have a power plant that is taken off the grid for some reason, stuff like that. How do we investigate this thing? So let me just simplify this thing, okay? I'm keeping the same left-hand side, and instead of this thing here, I'm linearizing, again, I'm a physicist. Nonlinear phenomena are very interesting, but first of all, you look at linear phenomena to understand them better. Okay, and I linearize things when I end up with some matrix here. That's the matrix Laplacian of the network grid. Okay, now it's a discrete Laplace operator. That's what it is. And this equation here, in that case, it's a wave equation. It's a wave equation with some damping, but it's a wave equation. It's a wave equation if I is large compared to D. It's a diffusion equation if D is large compared to I. But let's not go into these details. How do we see that it's a wave equation? Well, let me show you something that may be of interest here. Something bad happens here. Gaussian was taken off the grid, not for real, in my simulation. And one big nuclear power plant in Greece was taken off the grid. And you see what happens in terms of the frequency, how it goes down. What difference do you see between the two? At long time you don't see much. Well, you see something now.
Greece was worse.
Was that?
Greece was worse.
In what sense, worse?
Greece was
There were bigger oscillations, right? Let's have a look again at the initial time. So you see that here it's basically a frequency that goes down almost homogeneously. Here you have a wave that propagates and goes to Spain and then bounces back. So that maybe in that sense that you meant Greece was worse. And right, let me show you some snapshots here instead of this movie. Snapshot of, that fault in Greece, half seconds by half seconds up to 2.5 seconds. And what you see then is that the frequency fluctuates very fast here because in that region we see that there is some power missing. And then the power missing, is the information propagates like a wave until you get to Spain. But there is this whole strip here that is almost never touched. Why is that so? And that's the place where, there was the Gaussian plant, actually, that was taken off in the other simulation. Well, it's a wave equation. It's a little bit like a wave. If you had a pond, that would be with the shape of Europe, and that would be much deeper here. The wave would be reduced in amplitude there, and then would come back when you go to the shore, let's say, more shallow waters in Spain. And it's exactly what it is. And you can relate the depth of that fictitious pond with the connectivity of the grid locally. Okay,
Like, connectivity is just density of the grid, or what is?
Yes. Let's leave it at that for here. There's a mathematical definition. Okay, so now let me skip this here. These were the topics that we investigated over time. Now, I want to look at something here, because I have this nice numerical tool. I have this model of the power grid of Europe. I have different power stations here. In black, you have coal-fired power station. In orange, you have nuclear. In blue, you have hydro, and so on and so forth. And I'm going to use that model to actually generate a fault. One power station in Spain is taken off the grid. And I look at, what is the response of the frequency of the grid in various scenarios. This is not the real grid, so I can actually play with it. And I reduce the inertia. I reduce this II here, going from orange to, I increased going from orange to green. And what you see is that the response at short times is strongly reduced with inertia. So what inertia does to you here in this power grid is the following. It absorbs this fault. If you have an unwanted event, if something bad happens to your grid, the first response is given for free by physics when you have inertia. You don't need to have control. You don't need to have an operator reacting. Just the rotating masses are slowing down or going faster, and they absorb these things. If you have many of them, the response is mitigated compared to if you have few of them. At long time, on the other hand, the difference is not very much. It's fine because at long time you have time to actually react. So that's the thing. I think that's the main thing. Old versus new productions. The old ones are mechanical. There is this electromechanical coupling between these rotating masses and the frequency of the grid. And so when you have something bad that happens to the grid, at short times, inertia is kicking in for free when you have these rotating masses, and not so much if you have new renewables. So that's the challenge, to incorporate these new renewables to the grid. And it's much less trivial than actually having this balance between production and consumption with the fluctuations.
I have a question. So how come that wind machines don't have a rotating mass?
They have a rotating mass, but it is not coupled to the grid.
It's not?
Wind turbines, they produce electricity, the current that comes out of them, if you don't treat it, it would be really bad. It would go up and down and fluctuate a little bit and so on. So you have power electronics that actually takes that current and first changes it into a direct current and then makes it into an AC current with the right voltage and the right frequency. And in these two conversions, you lose the coupling to the rotating mass of the wind turbine. But it's a good question because now there are people who actually advocate that we change the way we operate and control these wind turbines so that we make use of their mechanical inertia. And when you have like giant parks of wind turbines in the North Sea, it may be worth doing it. Yes.
I once heard that you can also use rotating objects to store energy.
That's right.
Wouldn't it be like a solution to combine this with the grid?
Well, inertia wheels, as of now, they are used for control only. There are very few of them, and they are used for very specific roles. But it may well be the case that we will use them more and more in the future.
Like for energy storage?
Not necessarily for energy storage, but for control. Okay. For grid stability.
But for storage, they're not such a good idea?
What's that?
For storage, they're not so great? Or?
Well, I mean, in a big rotating mass like that, what you store is few tenths of kilowatt hour, I guess. A few hundreds of kilowatt hours. And it's big, right? But there are examples in Germany where they actually took off nuclear power plants from the grid, where they kept the rotating mass, and they're still connected to the grid. Which may or may not be a good solution in the future. We will see. I think it's an interesting idea to explore, regardless. Okay, so now the problem is this: if we take away traditional plants and replace them with new renewables, we will lose inertia, and we will lose this ability to actually absorb these bad events on short time scales. So the question is this: where should we keep inertia? Where should we actually add more? Where is inertia needed, and where is it not? And that's the problem we actually decided to investigate a few years ago with my then collaborator Laurent Pagnier. So we had that model. And the question we ask is, where should we optimally distribute inertia and also control these I and D parameters that we have in these swing equations? Well, the first thing is, what does optimally mean? Okay, so what we do is that we define a cost function. See, the cost function is an integral over time of a quadratic form of the frequency. Okay.
So what is capital N?
Okay. Here, for instance, we took it's the inertia matrix, which we called M in that paper. And I'm not seeing it now instead of the I. Okay, so we
What
have.
size matrix is it?
What's that?
What size?
Inertia. Ah.
The inertia matrix, the II. It's a diagonal matrix with the inertia on each of the nodes.
Okay.
Okay, so that's the cost function we define. It's related, if you want, to the area below, between the horizontal axis and the frequency variation.
What's W?
It's omega.
Omega. What's
It's the
omega?
frequency.
Oh, okay.
It's the frequency of the grid. Yeah, actually I had theta dot before. My bad. Okay, now so this M here, we want to minimize it with respect to different distributions of inertia and damping, this control term. So the control is here. Inertia, unfortunately, is now M in the paper. I did not realize that when I was preparing my talk. But anyway, you have constant terms, and you have deviations, and you have these parameters AI and RI, which can go from -1 to +1. And at one place they can be -1, another place they can be +1, they can have intermediate values here and there. We want to optimize their distribution. And it's easy to do that. Oh, there's a constraint. I mean, optimization problem always have constraints.
Sorry, what is MI? The first one, what?
It's inertia. You have a problem with inertia, right? I mean, the mapping is II goes to MI. Okay, and M is a matrix which has M1, M2. Okay? Yeah, that's what happens when you take formulas from different papers, I'm sorry. Okay, I give myself a constraint in this optimization problem. Look, I cannot do whatever I want. There's a cost to actually reduce inertia here and change inertia there. The cost is this. I have that plant here, it's a big plant. I want to increase its inertia. I need to put another turbine. It's going to cost money. So there is this budget here, B, which I give myself. And what I pay to deploy this delta MRI, delta gamma AI, is going to be a sum of what I pay to construct new inertia, to construct new control, and to withdraw, to take off some inertia and to take off some control. Now, calculating that optimization function is in principle really easy. You have your differential equation, you made a modal decomposition over the modes of the graph Laplacian. You pull, you push, you get the answer. Except it works only if you have a single set of modes that is valid. That means if L commutes with the other matrix.
Expansion means along eigenvalues.
Along eigenvalues and eigenvectors of L.
Okay.
But it works only if that matrix commutes with the other two matrices. Because then they have the same basis. And roughly speaking, what that means is that I and D must be multiple of the identity matrix. That is, you have a homogeneous situation. And we don't want to have a homogeneous situation. So we remember that we are physicists. What we do is perturbation theory. Perturbation theory, you have a matrix whose eigenvectors and eigenvalues you know. Can you actually approximate the eigenvalues and eigenvectors of a slightly different matrix, mu being a small parameter? And the answer was given by Erwin Schrödinger when he was not torturing cats in the form of a series expansion, and I give you only the first few terms. So, this is called Rayleigh-Schrödinger perturbation theory. It's very well known in physics. I mean, you do that in kindergarten physics when you have your first class in quantum mechanics. And then you send your paper to an IEEE journal, and the referee tells you that if such an easy method existed, it would be known.
Wait, you sent it? It's what you sent or Schrödinger sent?
Was that?
That was what you sent? Oh, what Schrödinger said.
No, it's not what Schrödinger says. You know, Schrödinger is long dead, right?
No.
Like his cat.
I know.
He didn't exist at Schrödinger's time.
No. Look, in Schrödinger's time, I think that, you know, referees, if they existed, they may have been more reasonable, at least, you know, that's what I would think. Or at least they would think twice before saying that to referee. No, we send it to you know, it's a good journal, but it's an engineering journal, and the referee didn't know about that method, and he thought that if he doesn't know it, it doesn't exist. That was the answer. Okay, we made a point referring to some textbooks that it exists for a long time, and the paper was accepted, happy ending. Okay, anyway, I'm not going to go into the details of the calculations we made, but what we got was this. If you look at distribution of inertia versus budget, you have 4 points. They are represented by these 4 snapshots: inertia, damping. Damping is control, if you want. Okay. So at the beginning, with relatively little budget, you see that it's yet another notation, your optimization function goes down quite a bit with very little budget and without changing the inertia. So basically control does this, but not inertia. You should work on control. You should not worry that much about inertia. Of course, what this means, the initial situation is the situation where inertia is homogeneous. So what you want, the message here is that inertia should be kept constant. Well, more or less homogeneous all over the grid. And if you really want to get the last few percent of your cost function, then eventually you may want to actually add or subtract a little bit of inertia. Red means subtracting, blue means increasing. But you always increase control. And that's one of the results that we got. Keep inertia homogeneous. Well, first, okay, it was 96% of the effect. Doesn't require you to change inertia. And then second, keep inertia homogeneous. That is, if you take off a plant here and you put some, photovoltaic plant, massive one, you better make some rotating mass nearby or something that actually emulates inertia. There are some things called like synthetic inertia based on storage that allow you to do that. But I'm not going to go into this. And control is actually more important. Okay, so that was our result. We are very proud of it. That's why I went into some technicalities here to show you that. The bottom line is that I do not think that the problem is it is complicated, it is complex, it is distributing inertia over many different countries. There are political things involved, but I mean, it's not a truly deep down technological problem. We have the technology to actually do it. Okay, so that's sort of like a summary of what I did here today. Electrifying your energy sector means increasing the electricity demand. And of course, there was the case that was made in the first talk this morning that actually we should try and reduce our electricity demand or energy demand. And I'm not against that. I'm actually in favor of that. That's for sure. But you consider the worst case scenarios, and we consider that electricity demand is constant. And if it works for constant electricity demand, or even increasing electricity demand, it will certainly work if it goes down. Remember that you need to produce your electricity cleanly, right? It has absolutely no sense to actually drive an electric car in Poland nowadays because, the electricity that you're going to use has been, generated by coal-fired power plants. There will be a significant increase of fluctuating non-dispatchable new renewables because we want to produce electricity cleanly. Remember that, if you are told that actually it's very hard to absorb these fluctuations, it is hard, but it is not impossible. And actually grid operators already know how to do that. They probably will have to actually, build new infrastructures, but they know how to do it. So you will need to have resources to absorb unavoidable faults, bad events, as it was said. And the good news is that inertia, which is that thing that physics does for you, is not necessarily the most critical thing. Actually, it's control, and control, we know how to do that. We have control theorists that have been working for decades on that, and they know how to implement these things. It may cost something, but the technology is there. Speaking of which, it may cost something. I haven't said how much it would cost. It's not my business, and it may cost a lot, but by the end of the day, investing in infrastructures is not necessarily a bad thing. Okay. Last conclusion. So we are in the middle of that crisis with, safety of electricity supply that is threatened. Let's remember that. When written in Chinese, that's what John F. Kennedy, of course, he was campaigning probably when he said that, but I think it's a nice word. When written in Chinese, the word crisis is composed of two characters. One represents danger, the other represents opportunity. When we are facing a crisis, let's be aware of the danger, but let's recognize the opportunity. So let me finish with a optimistic, actually, message, semi-optimistic. There was the World Energy Outlook 2022 that has been published a month or two ago by the International Energy Agency. And what they said is that, well, there seem, things, at least pledges and commitments from countries all over the world indicate that, renewables see sustained gains. The upside for coal from today's crisis is temporary. The increase in renewable electricity generation is sufficiently fast to outpace growth in total electricity generation. It will drive down the contribution of fossil fuels. So we are not necessarily totally on the wrong track. It needs to be confirmed, but I mean there is hope, and I think we need to whenever we have some optimistic message, let's have a look at it and keep it in mind. Okay. Thank you for your attention. I'd like to thank my institutions and my funding agencies and people here that worked with me, including Robin, who is here. And I'm ready to take your questions.
Thank you very much for this nice lecture. Are there any questions, comments?
How do you implement control for renewable energies? The classic, you can't turn on wind or something.
No.
But how do you manage the control aspect?
Yeah. So, of course, you can bring down the production at will.
Yes.
But you cannot increase it, in principle.
Mm.
So there are different, suggestions that have been made. The first one, of course, that comes to mind is to actually couple this to storage nearby. Okay, storage could bring up the production almost instantly if you want. That may be costly, but that seems to be working. The second possibility is to actually require at some times of the day when some conditions are met, and that would be the choice of the grid operator, that actually wind turbines, photovoltaic panels would just produce at half what they could, so that they would have the flexibility to go up or down. Things of this kind. And there are many other schemes that have been proposed. And of course, asking a producer to not produce everything he could means, you need to come with some financial incentives.
So there the idea would be just to have enough room to wiggle in.
Yeah, that's right. That's right. And there are more sophisticated schemes that have been proposed, of course. That's one of them. And of course, what that means is that there should be an electricity market for such ancillary services. I mean, you need to pay the person to be ready to produce more if needed or less if needed. That already exists, but that is not very well developed.
One, two.
This would actually fit. So in talking about storage, suppose all producers go down, how long could you envision storage to last for, say, Switzerland? I mean, if you build some storage facilities, how long could this last to supply?
If there was, okay, so
like seconds or
at
hours?
what level? At the European level or at?
Even Swiss or European, it doesn't really matter.
Well, okay, so the storage we have when the dams are filled in Switzerland, this is basically 10 terawatt hour, 9.
And that lasts for how many hours?
9 is about 14% of the annual consumption of Switzerland. Annual consumption is 60 plus terawatt hours. So it's
very long.
There's a factor 7. So in principle it can be done. But now if you look at the at the grid that I showed you here, many of these dams are injecting into the red or the green power grid. Basically, every power station in Switzerland is about 100 megawatts injects there. Okay? So what that means? Well, electricity will flow on that grid according to Ohm's and Kirchhoff's law. So there's no stopping it from going to France, to Germany, to Italy, or to Austria. You know, at some point in the beginning of this crisis, some people were saying, you know, we risk the blackout because we have no agreement with the European community. Well, they cannot stop electricity from flowing into Switzerland. We have like 21 very high voltage power lines connecting Switzerland to Europe. You know, the total capacity is about 15 gigawatts. 15 gigawatt of capacity. That's 50% more than the top, the peak load that we have in Switzerland. You know, there is no way they can disconnect us. Or if they disconnect us, they disconnect Italy. And that would be bad. So I mean, we're in the same boat. We're in the same boat.
Jeroen and then Michaela.
Yeah, I was wondering for the storage, if there are enough electric cars connected to the grid at any time to charge. Maybe you can charge more if it's sunny and windy, and otherwise charge less. Like you can use this battery that's available.
You know, the thing with cars is that they are not used more than 5% of the time or something like that, I think, on average. So many people have thought about that, and there are N+1, you know, investigations of this type of things. How could we use these batteries, you know, as some sort of storage? You know, think in terms of number of vehicles you have in Switzerland. I mean, you know, if you have like millions of cars, each with 50 kilowatt hour, you know, that's a significant storage that you have, right? That's 50 gigawatt hour. And so, you know, you could use that. And of course, you know, many people have looked at that. But then, you know, how can you effectively do that? You need to have a contract with the person who has the car. Right?
Yeah, or a product or a contract with the company that built the car. I don't know.
Yeah. You know, when you go and you ask a Renault for a car, and they will tell you whether you sign or not the contract, whether you give access to your battery or not. That would be one thing. I mean, you know, as usual, the implementation, the complexity of the implementation is more human than technological.
Peer-to-peer batteries.
Yeah, like that. You know, right now, when you take your electric car, you connect it to your charging station. You know, power can flow in but not out.
Michaela?
So I think you said that you take into account the hypothesis that the demand in energy will increase, but I think that pretty much everything I've read says that if we keep the energy consumption we have today, it's just impossible to replace, like to do this amount of consumption only with renewable energy. Like we would have to cover Switzerland all with photovoltaic and wind energy, and it's just not possible to produce so much energy.
Okay, so I am sure that there are many people who say that. Okay, I don't know about other countries, but I know that there's been a study by the Swiss Federal Office of Energy, And what they have is that, you know, there are sufficient roofs in Switzerland to accommodate enough photovoltaic panels for the consumption. Of course, you know, that would mean peaks of 20 plus gigawatts of power every now and then, which is not something that is easily mitigated. So there needs to be, you know, some control to actually shave this peak away and stuff like that.
And is nuclear power usually taken into account as well, or?
Sorry, say it again.
Nuclear power, is it also taken into account in these kind of studies, or when you talk renewable, is it just photovoltaic?
Well, you know, at this point, everything I showed you was with nuclear power plants as they are now in Europe. Okay, we did not take them off. You know, one study we did, though, is that at some point, you know, the Swiss political system is such that every now and then we vote for one object or another. And when was that? 2016 or 17, I think. In December, there was a vote on whether we would shut down the Betznau 1 and 2 power stations immediately. And the study that we made was that, well, guess what? If you do that, you know, eventually that electricity that they produce is going to be produced by a coal-fired power station somewhere in Germany or by a nuclear power plant in France. So what's the gain here? I'm not in favor of nuclear power plants, but I mean, you know, we can actually use those that are already built as long as it takes to actually bring up new renewables and then shut them down.
Okay, but it's
not build a new one, that's for sure.
But it still should be possible to, I mean, if eventually we wouldn't need them, like, I mean, we could do enough renewable energy so that we can even stop nuclear plants we already have now.
I need to be more careful about this, right? Because, you know, Switzerland is blessed with, you know, hydropower in the mountain, you know, which is, you know, here in Chamozon, you have like 2 gigawatts, well, here around you have like 2 gigawatts of power that can be turned on or off in a matter of minutes. Okay, and so that's very helpful. So I think for Switzerland, we could do it. For Europe, it's a different story. Right? I mean, you know, Belgium and the Netherlands don't have, you know, amps.
Well, there is some.
So that's harder for them.
I have a question. Is it possible to just cap consumption?
You just have
Cap consumption? Cap consumption?
gas consumption?
No, cap. Give a upper bound on the
Yeah. That's what I was saying. You know,
individual
peak
consumption.
shaving is something that is often considered, right? If you put a lot of photovoltaics, eventually, you know, you may overshoot your consumption by a lot. So you just shave the peak. Okay. Now, of course, again, the devil is in the details. How do you do that? I mean, you can do that by just turning a knob, but I mean, you know, the person who produces and who expects to be paid for a production, that person is not going to be happy if you turn off the production, right?
So now you're talking about capping production.
Yeah.
I think the question was capping consumption.
Actually, you see, here I have.
I was asking about capping.
Yeah, you see here. This is photovoltaic. No, this is wind in Arizona, and it is clearly shaved.
But that's production again.
Yeah.
And the question was about consumption.
Ah, you meant consumption?
Yeah.
You mean turning the light off?
Well, yeah, you allow some like minimum so that people can have important stuff that they sustain in some stuff, but then you cut out the rest. You decide on a budget for everybody.
Well, okay, so this is being discussed in the current crisis, but I don't think this is a long-term solution, right?
You don't think it's a long-term solution? Why? Like, people learn to live within the limits when they're capped, right?
You know, the acceptance in the population is not going to be there, right? I mean, the first thing you want is advocate for something that can be accepted.
Okay.
I think.
But loading electric cars could be more or less directed. I mean, you may load them when there is too much electricity. If you accept, if you're not in a hurry to fill it.
No, but that is okay. So I understood your question as being, you know, you force this. If you go up, you know, at some point you cannot turn on the light anymore because you're already at your quota. And this is
Yeah, but if you put a quota, like then people.
There are things like demand-side management. It's how it is called, which actually, makes you consume some electricity at different times.
Right.
Give an example. Now when you take your shower, you have your water is heating right after you took your shower because there was a lot of cold water that went into your boiler. Well, you could delay that because you take your shower in the morning and then you go to work. You could delay that by several hours at a time when, for instance, your photovoltaic panels would be producing. Same thing for other appliances. So that's a solution. That's an interesting thing. Yes.
Just as a brief follow-up, I mean, you cannot so easily just cap the consumption for like an arbitrary person, right? I mean, that's really the point, that you just have energy in the grid, and capping would just mean the person, like that we have blackout somewhere, but not like for a specific person, right? So that would mean you have to control the devices, as you just said. Or do I misunderstand it?
Well, I mean, we are going very far in a longer road that I'm not sure I understand quite well. Oh, look, there have been discussions, right, about capping, and all these discussions, as far as I know, have been made in the context of, emergencies, not normal procedures, not, standard operation.
And it just meant really technical. How does this even work to cap?
Okay.
Technical level, that's how.
Oh, well, I mean, you can cut an entire district.
Yeah,
Geographically.
I was thinking something less drastic, so that
And that's really my point. I mean, I thought it's just really not easy to just cap.
Yeah, that's the thing. That's the thing. I misunderstood. Yeah, that's the thing, right? I mean, they cannot decide. The grid operator cannot decide to actually turn off. I don't know, your whatever video game and let you cook, right? They cannot do that. They turn on or off your entire house. Now, the thing is that there are a number of appliances that nowadays, for instance, heat pumps, when they install them, they are fully loaded with some, smart things, that's what they call, meters and power electronics. And in principle, they could be remote controlled. But as far as I understand, it has never been really implemented in real life.
Okay, Martin.
Yes, just a question about hydropower. As glaciers are retreating now, we might build new new dams in Switzerland. How long would it take? I mean, we are talking about one new project in Zermatt, for instance.
Yeah.
How many years do you think it takes from the start of the project until it's sort of usable?
Historically speaking, between 5 and 10 years would be the answer, I guess. That's historically speaking. And we don't seem to be that much faster when it comes to civil engineering that we used to be in the 50s and 60s. I would say so, but, I guess it depends on who you ask, and you should ask a civil engineer, but I mean, it's not a short-term solution.
Yeah, how much is to be expected from improvements on technology? I mean, for instance, in solar panels, they're becoming more efficient, or storage can be done by batteries, but can be done by pumping water. So batteries are improving by a lot in a decade. So it is taken into account, or is it, or we already have the good enough technology to implement all this?
I think in terms of batteries and power electronics, I mean, we don't need to go faster than what we have now. Of course, the price can be improved, and it will be, it will go down. Of course, there will be economy of scales because suddenly you produce more, right?
I know, for instance, the
price, but not in terms of performances. I mean, to give you an example, there was a blackout in Australia. You've heard of that Tesla storage plant that they have there. It's not that big, but it's several tens of megawatt hours. And so there was a tiny bump in the frequency of the grid. There was some small problem somewhere, which was identified by this very efficient power electronics as a major problem, which actually kicked in immediately, you know, like tens of megawatts, 30, 40, or 50, I forgot what are the numbers. It went in so fast that the old control measures identified that as a major failure. And so they disconnected everything. There was a blackout. Okay, so I don't think that the performances of these devices are really need to be improved. Actually, what we need to do is actually to make them compatible with what already exists in the grid. In terms of, yeah, pump storage is also a relatively old and mature technology, so I don't think it can really be improved in terms of efficiency. And you mentioned something else? There was the third one, I think.
So about the wind turbines, I know they are building bigger and bigger turbines and putting them offshore.
Yeah. So this is always, but you know, it's still the same thing except to make a bigger construction. Right?
Is going to make any difference for the model, saying, okay, we have this kind of technology?
Well, no. In our model, what we have is basically these values, right? I mean, you know, how far can you go? And if you have a bigger wind turbine, you can go there. So the injection of power is going to be larger. Maybe one thing, though, is that, you know, you would expect that if the turbine is larger, then the production would not fluctuate that fast. Right? I mean, sometimes you see fluctuations on the scale of 15, 20 seconds. And if you have really that huge piece of metal, it's hard to think that they would slow down that fast.
Last question by Thibault.
It's a very small one. I have no idea of the abundance of materials which are necessary to build photovoltaic panels, this kind of stuff. Is it an issue or not if you want to electrify Switzerland or Europe?
Yeah, so, well, you know, the short answer would be I don't know, because I'm not an expert in that field. And of course, you heard about, you know, different answers to that questions, right? As far as I understand, many, if not most, for instance, lithium. Lithium exists in Europe. There's a lot of lithium in Europe. There's no mine. That's it. Right. So if we actually needed lithium to have lithium-ion batteries, we could mine it in Europe. It just so happens that there are mines in China and in Chile and I forgot where else. So by the end of the day, for the first time, which is good, for the first time we have a new developing industry and people ask the right question that they never asked for any other industry before. Right? I mean, you know, when they tell you about photovoltaic panels, how are you going to recycle them? Well, guess what? How are you going to recycle your nuclear power plant? Okay, so they never even discuss that. Okay, so these are good questions, but it's totally unfair to take them as a no-go question. That is for sure. And when it comes to, you know, again, minerals, as far as I understand, a number of these minerals actually are rare because they haven't been pursued that much so far. I may be wrong, I'm not an expert. Okay.
Thank you for your answer.
Okay, so let's thank Philippe again.